Hello everyone. So today we're going to look at an aspect of objects that we have really kind of neglected up to this point. Whether you realize it or not, up to this point we've kind of dealt with all objects as being particles, if you will. We thought of all pieces of them as kind of moving together as one big thing. Even when they didn't, say a cart that has wheels that spin, we kind of ignored, right, the spinning wheels and just dealt with it as being a block, right? So for the first time, we want to look at some things maybe that aren't just particles and look at that aspect of it. So consider a meter stick. Well, we could treat the meter stick as if it was a particle, but it might be a little harder to do if we twirled it, spun it, if you will. If this meter stick is spinning, you might notice that different pieces of the meter stick are going in different size circles, even though the whole thing is taking the same amount of time to go around once, which means different pieces of this meter stick are going at different speeds. Right? They're moving at different speeds. Right? Different size circles, same amount of time. And so if we want to deal with the meter stick as an actual object, we have to deal with the fact that different parts of it move differently when it spins. Imagine that not only is it spinning, but it's moving as well. Now the motion is getting even more complex. A point on the outside is going in some sort of loop-to-loop kind of thing as it goes across the screen. But if you look, there is one point on the meter stick that seems to be moving like a particle. See that point? If you look at that point on the meter stick, it's just moving in a straight line at constant speed. While the rest of the meter stick is moving in circles and moving to the right, little curly cues, if you will, the point here is just moving as if it was a particle. Oh, interesting point. This point has some different properties. Okay, this point is special because it's the balance point. And if we were to take the meter stick, there's only one point that we could put a fulcrum, fancy name for this thing, right? Fulcrum, underneath that would put this thing in balance, or put our finger underneath it and get it to balance and not fall over. That happens to be the same point. If we threw the meter stick through the air, that point would actually travel like a particle. It would move in a parabola. See the parabola it's moving in? Right, the rest of the meter stick isn't doing that, but this point is. In fact, so that means that that point acts like all of the mass is concentrated at that point. And if we shrunk the meter stick down to a point, right, we'd have to shrink it down to that point, and then it would move just like our projectile motion particle, right, in a nice parabola, when only gravity is acting on it. This is what we call the center of mass of an object. Center of mass. It's technically the point on an object or system of particles which acts as a simple particle. It's where we can think of all the mass of the object or system to be concentrated. It's the point that moves as if all of the external forces were applied to that point. Right? If the force of gravity was applied to that previous meter stick, and that's it, right? That point acts just like a projectile. And it's the balancing point. This one's kind of important from an experimental standpoint. If you want to figure out where that meter stick balances, right, you might use the edge of the table or your finger or something like that to figure out exactly where it balances, and that would give you at least an idea, a good approximation of where the center of mass is, depending on how well you can do that and how much of a good knife edge you have to put it on. So let's see how we can figure out where the center of mass of some particles are. We're going to do this in one dimension and then two dimensions in this video. So here we have two masses, mass 1, mass 2. they're tied together by or connected together by a thin massless rod. Now, we do this a lot in physics, all right, so that they are connected to one another, so it becomes like a barbell kind of situation, but we're going to ignore the rod for right now. That makes it much more difficult. We'll get to that, but it makes it much more difficult to include the rod. Now, obviously, we can't create an actual thin massless rod that's going to be rigid enough to, if we wanted to balance this system at a point, but maybe these are several kilograms each, and this rod is made out of, I don't know, plastic or aluminum, so that it's very light, right, compared to the masses. Then it would be a decent approximation to say it's massless. Maybe not perfect, right? It might be a little experimental error if we figured out the center of mass or balance point here, right? And might be slightly off because of the rod. But unless we want to get several sig figs away, good enough of an approximation. So I'm saying the center of mass of this situation is about right here. This is where it balances. Okay, so this is the center of mass. Now, looking at my diagram, how do you think these two masses compare? The mass of object 1 and the mass of object 2. And don't look at their size. I never said they were made of the same materials. Right, so this could be lead and this could be aluminum. Look at the center of mass and try to decide how the two compare. So think of this as the balancing point. So yeah, hopefully you're saying, well, because the center of mass is closer to this object, it's got to be more massive. M2 is more massive than M1. Yeah, I made it bigger too, but it's not volume, it's mass. It's a density, if you will. Right, so yeah, if the center of mass is closer, this must be the heavier side, if you will, the more massive side. Now, how can we calculate exactly where it is? Well, we have to put a coordinate system through there. So notice I'm putting my 0, 0 of my coordinate system at the center of the object, the M1. And we're going to really run center to center here. We're going to treat these as if they were particles while finding the center of mass of the system. I know, but it works. At least in introductory calculus-based levels. So let's call this distance d, from the center of M1 to the center of M2. This is what might be called the separation, if you will, of the two masses. They're separated by a distance d. Then my claim is this is the equation that we would use. Okay? Now, I'm just pulling this equation out and giving it to you. I know that's weird. I usually derive it or we do an experiment. Don't have a good experiment to do this, and very hard to balance things in lab. Right? And the proof for it really takes rotation, which we're not in yet, so we'll revisit it then, right? But I want you to kind of buy this from example, if you will, that this works. I'm saying that the position of the center of mass is M2 over the total mass, M1 plus M2, times the distance, the separation. So let's take a couple of examples here and see if we can convince ourselves that this equation works. What if the two masses were both M? What if they had the same mass, in other words? Well, then we could get rid of the subscripts. And notice we have M over M plus M. Well, M plus M is 2M, right? And M over 2M is 1/2. Please, M over 2M is not 1 over M. Right? The M's cancel and we leave the 1/2. Think of your algebra. So this equation is predicting that if the masses are the same, the center of mass would be right in the center. Well, that kind of makes sense, right? That works. Well, if M2 is bigger than M1, M2 is bigger than M1, then wouldn't this fraction be bigger than 1/2? Right? Which means the center of mass shifts towards M2. The bigger M2 gets, the more the center of mass shifts towards M2, which I hope makes logical sense. If M2 is a lot bigger than M1, this fraction eventually just becomes 1. Right? If M2 is way bigger than M1, if you're saying like M2 is 100 kilograms and M1 is 1 gram, right? Well, 100 over 100.001, right? An extra gram is essentially 1, and the center of mass would move right into M2, which also, again, kind of makes sense. So this equation, in other words, does work. Right? You're going to have to play with it a little bit here in things we do in the next day or two in order to kind of get it down. Okay, and this is one version of it, and this comes from a nice placement of the axes, right, where I put them right through M1. But what if we put the axes out here, just somewhere in space? Now, I am going to try to keep this one-dimensional to make our life easier. We'll talk about multi-dimensions in a moment. But what if it's out here? Well, now we can say that M1 is at a position x1, M2 is at a position x2, and the center of mass is at a position xcm, which stands for center of mass. I've sometimes even seen this COM, center of mass, right? So this is the position of the center of mass from this axis. This is the position of object 1. This is the position of object 2. So hopefully you see that the equation would expand, if you will, to this. M1x1 plus M2x2 all over M1 plus M2. Now, first off, just to help you believe that this is the equation, if we shift the axis back, right? If we shift the axis back, notice that that just moves all the things back and it becomes the same equation, right? x1 becomes 0, so that drops out, and it becomes our previous equation. Note that if one of the objects disappears, if all we have is M2, right? M1 is 0, cancels out of there, cancels out of there. M2 over M2 would cancel, and we have that the center of mass is at x2, which certainly makes sense. It's right at M2. If the masses are both the same size, so that again we could say M, right, for each one of them. Notice I got rid of the subscripts. Well, I could factor out an M. Right? So notice this is, remember, M plus M is 2M. So if I factored out an M and canceled, I'd get this. And notice, what's x1 plus x2 over 2? Well, x1 plus x2 over 2 is the center of M1 and M2. Right? It's right in between. It's exactly in between. So note, this tells us that the center of mass would be exactly in the middle, which again makes sense if the masses were the same. So this is the equation we're going to use. This is for two particles in one dimension. Note that what we added to this equation, right, to get back to this one, is an extra mx, right, for our other object. So this is a more generic version, right, of the equation in one dimension. In a more general system of n particles, we would have to add an mx for each particle. In other words, it would look like this. m1x1 plus m2x2 plus all the way up to mnxn, where these are the nth particles. Right? So if there were 20 particles, we'd have 20 mx's. And this is still just the total mass. Right? We're just adding up all of the masses that are involved. Now, this is nice, but we can write this in a little bit better notation if we use summation notation. So first of all, here's 1 over capital M. Be careful here. I'm using little m's as the masses of the particles. I'm using capital M to mean the total system mass, which is the sum of the masses of all n particles. Okay? So capital M here is a total mass. Important that you get that. Right? This Greek letter sigma means sum, summation. What do you do with this when you sum something? You add them together, right? Like we're doing up here. Now, technically it's a vector sum because this x is a vector, it's a position. So it could be positive or negative. It depends on where we put our coordinate system. Although, make your life easy if you get to choose, try to make it a positive coordinate system. But I could have gone back and made M2 R0. Then M1 would be at a negative position, right? Because it's to the left of 0. Okay, so this is the better one-dimensional equation. And we'll do a couple of examples of this so you can see how I can expand this summation out. So it's 1 over the total mass times the sum from I equals 1 to n, where n is the number of particles, of all of the mi xi's. All right? This I equals 1 to n basically tells us how many mx's we're going to have because of how many particles we have. Now, if we had 3 dimensions, we just have to use 3 of these equations. Right? There is one position of the center of mass in a 3-dimensional system of particles. It would have an x position, a y position, and a z position. Right? So we already talked about the x, the horizontal. The y is 1 over the total mass times the sum from I equals 1 to n of all of the mi yi's. Right? That's the vertical position. And the z center of mass is 1 over the total mass times the sum from I equals 1 to n of all of the mi zi's, where zi is the in and out position. Positive out of the screen, negative in to the screen with a conventional right-handed coordinate system. Now, because we can, in unit vector notation, write our position as xi cap plus yj cap plus zk cap. Remember that I, j, and k are unit vectors, which means they have a dimension of 1. Right? They have a size, a magnitude of 1. They're all about direction. Right? I cap is horizontal, j cap is vertical, k cap is in and out. I, j, k, x, y, z. Right? Alphabetical order. We can write the center of mass in one single 3-dimensional equation as this. The 3-dimensional position of the center of mass is 1 over the total mass times the sum from I equals 1 to n of all of the mi ri's. Now, this is a wonderful equation to know, but we're really going to use these to do any of our problems, right, with a system. We'll look at this one and change it into more complex math in the next video. Okay, let's do a couple of examples. So here we have one mass that's 10 kilograms and one mass that's 5 kilograms. They're separated by 3 meters. Where is their center of mass? Right? If I had a thin massless rod running through them, where could I put my pivot point? If I threw the system through the air, which point would move in a parabola? Right? Which point would this rotate around naturally if you just spun it? Okay? Well, I'm going to call M1 10 kilograms and M2 5 kilograms just because of their size. Let's assume they're made out of the same thing. I can put my coordinate system anywhere. Well, let's make this a one-dimensional problem. And let's put M1 right at the origin. Why not, right? So here's the coordinate system I'm using. Again, you can really put it anywhere. It's just that some coordinate systems are easier than others, as you will see. And their centers are separated by 3 meters. This is the separation, right? So we'll go center to center. So, one-dimensional, horizontal. So the x position of our center of mass is 1 over m times the sum from I equals 1 to 2 of all of the mixi's. See how I put a 2 there because there's 2 particles? That means that we are summing, adding 2 mixi's, which if we expand it, would look like this. See how I got from here to here? I don't know how much summation notation you do in math these days. Okay. But I equals 1 to 2 means we're going to add up all the little mixi pieces, and there's only 2 of them. Now, given the coordinate system I chose, are any of these mixis 0? Well, sure. M1 is 0 because xi, or x1, sorry, is 0. Right? x1 is 0, so that's 0. So notice this equation just reduces down to the first one I had on the screen, right? That's why I ask you to remember this, right? Not the special cases. Plug the numbers in. Notice how the units work, right? The kilograms cancel. We're left with meters. So we basically have 5 kilograms over 15 kilograms. Right? 5 over 15 is 1/3. 1/3 times 3 is 1. So the center of mass is 1 meter away from our 0 point, which would be about here. Now, notice here the proportional thinking thing. Hopefully some of you are already looking at this and going, oh, it's twice the mass, and it's half as close, right? It's twice the mass, half as close. It's 1 meter away from this, whereas this one is 2 meters away. Yeah? So in simple cases, you might be able to proportionally kind of think things through, which certainly comes in handy on a multiple choice this kind of situation, right? But the equation here always works. So if we spun this, it would spin around that point. Right? If we threw it through the air, that point would go in a parabola. If we wanted a fulcrum, we could put it right under there, and we'd end up with it all nicely in balance. So 1.0 meters. Everybody okay with that? Now notice that this answer would change depending on where we put our coordinate system. If we put our coordinate system through the center, right, at about, at what would be 1.5 meters right now, right, in this coordinate system. But if we put it here, we'd get an answer that was only a half a meter away, right? Because the center of mass doesn't change depending on where the system is. Just the naming of that center of mass changes. But if you think about that, hopefully that would work, because then we wouldn't have a 0 here. We'd have 10 times negative 1.5, right? Because if we put the 0 here, this would be to the left. 10 times negative 1.5 and 5 times positive 1.5, all over 15, right? And it would work out to be 0.5, actually negative 0.5, right, to be technical. So why did I choose this system? Because it's easier, right? I created a 0 in that case. Always easier to put zeros, right? But we could really put this anywhere. We could slide it over here so that each one of these had a position, as long as we knew those positions. Heck, if we wanted to be really stupid, we could put it way out here and make it 2 or even 3-dimensional, right? But if we can reduce it down to a 1-dimensional problem, why not? Make your life easy, people. So here's a 2-dimensional example. Can't get away from the 2-dimensional of this. I spent a lot of time creating this example, right? We have these 4 particles of mass 1 kilogram, 2 kilograms, 3 kilograms, and 4 kilograms. Ooh. Right? They are separated by 2 meters vertically and 5 meters horizontally. Little rectangle shape, if you will. And I want to know where's the center of mass of the system. Now, if you could imagine these embedded in a thin plastic sheet, 2-dimensional, right? So that we could ignore the plastic, right? These are pretty massive, right? So we could ignore the thin plastic sheet, right? I'd be asking for, where would I stick my finger underneath this so that it would balance? Well, since this is a 2-dimensional problem, right, we're going to need to do it in 2 parts. Right? Take each dimension one at a time, which is something we've done with forces and with motion, right, all year. So we need to create a coordinate system. Again, we could put it anywhere. There's a bunch of places we might put it. I'm going to put it here. Notice I put my origin through the center of this object, the 1 kilogram object. Why? Well, because it keeps everything in the first quadrant, so it makes everything positive. Why make your life hard? Right? Choose to put it where you want it. Now, I'm also going to do something a little tricky, but this comes in handy on multiple choice problems, and in this class, because you have to be able to work symbolically. It's a little trick that you can use. Note that the masses are integer multiples of one another. So if I call the 1 kilogram object M1 M, then I can call the 2 kilogram object 2m, the 3 kilogram object 3m, and the 4 kilogram object 4m. See what I'm doing? And then I don't even care what the actual numbers are. I just care about the integer multiples. So this could be, let's see here, this could be 10, this could be 20, this could be 30, this could be 40. Right? And I could still use m, 2m, 3m, and 4m. And the center of mass would be in the exact same place, right? Because of how we divide masses. Okay. So let's start out with the horizontal position. Horizontal. So 1 over the total mass times the sum from I equals 1 to 4, because there's 4 objects, of all of the mixi's. So since it's I equals 1 to 4, we're going to have 4 of these in our equation when we expand it out. So you're hopefully asking yourself, are any of these 0? Well, let's look at the coordinate system I chose to use. 0x would be on the vertical axis, right? 0's right here, so anywhere on the vertical axis. So it appears that 1 and 4 are at position 0. Position of 2 and 3 are 5 meters away, right, horizontally. Okay, gotta think two-dimensionally here. So those are 0 in this case. And we know that we can call this mass 2m, and this mass 3m, and this mass 4m, and this mass m. So if we plug those all in and get rid of the subscripts. Note I also did something tricky here. Well, the position of the 2 kilogram and the position of the 3 kilogram horizontally is the same, right? It's 5 meters. So to make our algebra nicer, I'm just going to call this x and x instead of x2 and x3. You see where all the subscripts went? 1m, 2m, 3m, 4m. So that makes these like terms, makes it 5mx. Down here we get 1 plus 2 plus 3 plus 4, which is 10m. Note the m's cancel. This is why I did the little trick with the m, 2m, 3m, and 4m. And so I have 5 over 10, which is 1/2 x. If x is 5 meters, right, it's 2.5 meters. Now, since this is only one-dimensional, that would mean somewhere on a line at 2.5 meters, at x equals 2.5 meters, right, the center of mass lies on this line somewhere. Now, were any of you saying that without actually doing the math? Does anybody see why we could have skipped the math? Yeah, check it out, right? On this side of the line, we have 3 and 2. We have a total of 5 kilograms. But on this side of the line, we also have 5 kilograms. This is what is known as a line of symmetry. If you can draw a line to make the masses, the coordinates and everything the same on both sides, well, the center of mass is just going to be in the middle, right? Horizontally, this acts just like a 10 kilogram and a 10 kilogram separated by 5 meters. Right? The center of mass would be right in the middle. If you can use lines of symmetry, they are beautiful things. And so if I was doing this problem, say it was a multiple choice problem on a test, right? I probably wouldn't even do this part. I'd just look at it and go, oh, right? We can balance it right in the middle. So that means it's got to be at 2.5 meters. Cancel out everything that doesn't have an x of 2.5 meters. Now, let's look vertically. Are there any lines of symmetry vertically? No, because there's 7 kilograms up here and only 3 kilograms down there. Now, before we even do the math, right, they're separated by 2 meters. Would you expect the center of mass vertically to be at 1 meter, at less than 1 meter, or at more than 1 meter? Hopefully you're saying, well, there's more mass above, so the center of mass is going to be closer to the more massive side, so the center of mass should be more than 1. That's even without doing the numbers. Again, handy way to do multiple choice problems. But if we want an actual number, We have to set it up the same, except we use y's instead of x's because this is vertical. Again, it's 4 objects. It's a sum from I equal 1 to 4. So we have 4 my's. Are any of them 0? Any of them 0? Well, vertically, 0 y, if you will, is right on the horizontal axis. Right? That's 0y, given where I put the coordinate system. So it appears that x1, or y1, sorry, and y2 are going to be 0. So those two will cancel out. See how my choice of system made life easier? Plug in all of the masses, and again, I can do the little trick where these two masses are the same vertical distance away from 0. Right? They're both 2 meters away. So I can just call them y and y instead of y3 and y4. That allows me to throw them together. We get 7my on top and 10m on the bottom. The m's cancel. So we have 7/10 y. Notice that's more than halfway there, right? Plug in the 2 meters, and we get about 1.4 meters. So that means on that line. Right? That's 1.4 meters away from 0y. So where is the center of mass then? Well, it's where those two lines match up. It's right there. At 2.5 meters, comma 1.4 meters if you want the coordinates of the point. If we connected these 4 things with thin massless rods and threw it through the air, that's the point that it would rotate around. That's the point that would go in a parabola. If we embedded these in a thin plastic sheet that we could ignore, that's where you'd have to put your finger underneath to get this to balance. Right in the middle, this way, right, x, but up towards the top, right, vertically because there's more mass up here. Now, of course, we could also choose to write this in unit vector notation, which would be 2.5 meters I cap plus 1.4 meters j cap. Kind of a nice way to write it, right? The coordinates, essentially, of the center of mass. Positive 2.5 meters, positive 1.4 meters, put you right there. That's the 2-dimensional position of a center of mass. I've never actually seen them ask you for a 3-dimensional system of particles, but it could be done, right? You just have to know all the coordinates, which is why they rarely ask you, because it's hard to draw. So like in the last example, the center of mass doesn't have to lie within the object. Let's say that this is kind of like a, I don't know, a tire shape or a inner tube. Probably be easier, right? This is like an inner tube all blown up, right? It's a donut shape. Well, are there some lines of symmetry here? Sure. Isn't that a line of symmetry? It's the same on the right as it is on the left. Isn't that a line of symmetry? Isn't that a line of symmetry? Isn't that a line of symmetry? I mean, there's lots of lines of symmetry. So where's the center of mass? Yeah, it's got to be right in the center. Right? We spun this, it would spin around the center of it. Hopefully that's not a shock to anybody. Sometimes you can do the problems without any math at all with lines of symmetry. Sometimes lines of symmetry will just get rid of some of your math. But they're nice things to think about with center of mass. So, last example in this video. First time we're going to deal with something that's not particles. Here's a piece of plywood, which I'm going to say is uniform, right? So it's the same throughout, right? It has an overall mass of 20 kilograms, and it's shaped like an L, where this side is 90 centimeters, this side is 60, this side is 30, which means this side is 30, right? This is 60 right here. So we actually have a 30 there, a 30 there, a 30 there, a 60 here, a 90 there, okay? And I want to know where's its center of mass. If I spin this thing, what's it going to rotate around? Where do I balance it? Okay, no obvious lines of symmetry here, unfortunately. So a couple of methods. In method 1, I am going to conceptualize this as 2 objects by drawing a little horizontal line in here. I'm going to conceptualize this as this square and this rectangle. Now, why would I do that? Well, can't we find the center or the center of mass of this square and the center of mass of this rectangle without really doing any math? Yeah. The center of mass of this rectangle would be, of course, right in its center. Right? Lines of symmetry, if you will, would go here and here, right, and meet up there. Well, what's the coordinates of that? Right? It's 45 centimeters by 15 centimeters. I took off the units for space reasons, but 45 comma 15, right? 45 comma 15. Note here I put my coordinate system through the lower left-hand corner of the L, which is a good place to put it because everything's positive then. Where's the center of mass of a square? Yeah, right in its center. Oh, by the way, I'm going to call this M. Then do you notice that this is 3 times as big? So it would be 3M. You okay with that? You could use fractions. You could say the total mass is capital M. And then this would be, let's see, 3/4 of the total mass. And this would be 1/4. But personally, I don't like fractions in my fractions. So I tend to make the smallest one M and then integer multiples of the other ones when possible, right? But go ahead and use fractions if you like the fractions. This would be 3/4 M, and this would be 1/4 M. So the center of mass of this one is in the center, right, which would be 75/45. Again, think about it here. 60 is to here. This is 30, so half of that is 15, so it's 75, right? Same thing here, that's 30, half of it, again, is 15, so 45. And this would be a mass of M. Everybody okay with that? Well, now we can just treat this as a 2-particle system. One here and one here. Because that's what the center of mass is. Remember that the center of mass is where you can think of all the mass as acting, right? That's where you can kind of reduce all the mass down to if you want to turn it into a particle. So by choosing to put this line in here, we made it 2 objects of which we could find the center of mass relatively easy. And now we can do our math on these. Okay, now there's no nice line of symmetry here, right, to use. So we're going to have to do both parts. Here is the x position of the center of mass. Right, it would be 1 over the total mass, which remember is 20 kilograms, times the sum from I equals 1 to 2, because we broke it up into 2 objects, of all of the mixi's. So we have 2 mixi's. We have m1x1 plus m2x2. If this is our 0, 0 point over here in the lower left-hand corner, neither of these are 0, but we do have the x coordinates of them, right? 45 and 75. We've got the masses we can put in, 3m and m. So notice here the m's are going to cancel. Now, what does that mean? That means it doesn't really matter what the total mass is. It's how the mass is arranged that's going to help us with the center of mass, right? That's going to determine the center of mass. If this was a 100 kilogram uniform sheet of plywood, the center of masses of these 2 pieces would be in the same place. This would still be m of mass. This would still be 3 times the mass, right? So it all just kind of factors through. So up here then, or let's see, we've got 4m down here. The m's cancel. So we end up with, do your fractions, 52.5 centimeters. See what I mean by this way you don't have fractions in your fractions, right? So it's about 52.5 centimeters horizontally. Remember that? What about vertically? Same equation, but the vertical version. Again, 2 objects here, right? We're using this and this. Neither of them is 0, right? This one is 15. This one is 45. Plug everything in. Again, m1 and m2 are 3m and m. The m's cancel. Work the fractions. You get 22.5 centimeters. Where's that on our coordinate system? It's right about there. Do you notice where that is in relation to the center of masses of the 2 objects we chose? Notice it's on a line between the 2, right? Oh, yes, it's on a line between the 2. It's got to be. Because if we're treating these as 2 objects, as if they were 2 particles, right, the center of mass has to lie right in between, if you think about balancing them. And you notice how it's much closer to the 3m? It's actually, if you did the Pythagorean theorem or something to figure out this distance, right? It's actually 3 times closer to here than it is to there. If we wanted to write this in one equation, here's the unit vector notation. 52.5 centimeters I cap plus 22.5 centimeters J cap. On a test, they may ask it this way. They may put it in a chart or something like that form so that you have to find the two, right? So notice what our process was here. We took this weird-shaped object and broke it up into 2 objects of which we could find the center of mass. Those are the points where we can think of all the masses acting. So we essentially turned it into a 2-object system and then found the center of mass of that 2-object system, which ends up being the center of mass of the overall object. Now you might be saying to yourself, well, why did you choose that? Right? Why'd you draw the horizontal line there? Well, really I did it so that I would have to do all the math. We could draw our horizontal line anywhere. Right? For example, we could break these up into 4 squares. Right? That's kind of nice because they'd each have a mass of m, 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 and m. Right? The center of mass would be in the center of each one, and then we do the same kind of math but 4 objects instead of 2. But here's the best one. Do you see it? What if I did that? And I broke it up into this rectangle and that rectangle. Why is that nice? They're exactly the same, aren't they? They're the same mass. This is half of the L. This is half of the L. Now the center of mass of this rectangle is, of course, right in its center, which is 30, right? This is 60 long, right? So it's 30 comma 15. The center of mass of this one is in its center. Oh, sorry, I'm going to call that M. Center of mass of this one is in its center, which would be 60 plus 15, or 75, right? Up 30. And this would also be M. Well, given what we just did, the center of mass is going to have to lie on a line between those two. But where on the line between those two? This has a mass of M, this has a mass of M. Right. It would have to be right in the center of those 2 points. So now we just have to find the center. Well, how do you find the center? How do you find the center? You just add the 2 x's together and divide by 2, and that's the center horizontally. You add the 2 y's together and you divide by 2, that's the center vertically, and we're done. And notice we get the exact same results we did before. So there might be easier ways to do these. Why did I choose the first one? Because I wanted practice with the equations. But sometimes if you get a little crafty, get a little tricky, right, you can think through some of these. Right. Now, what if the object isn't a nice shape like this one? Or there's something else different about it? You know, that doesn't make it things we can break up into nice little pieces. Well, then things get a little harder, and the math gets a little harder. But I'm going to leave that for our next video.